Hello everyone and welcome back to System Dynamics World channel. I hope you are doing great today, and in this video I want to talk about an important topic in system dynamics, the type of system models. In simple term, system model are a way of representing how a system works, and so we can understand it, analyze it, and improve it. There are several types of system models, such as physical model, mathematical model, simulation model, and so on. Each type serves a different purpose, but together they help us to see the bigger picture and make better decisions. So let's dive in and explore this type in more detail. Before that, again, I say the way of connection between us is System Dynamics World channel in YouTube, my email, and my LinkedIn page that you can see in the picture. Okay, let's go. We will talk about the concept of model and why it's necessary. A model is simply a simplified presentation of a reality. We use it to understand, analyze, and even predict complex phenomena. And that's obvious that the real world is often too complicated to deal with directly, and so models help to reduce that complexity into something we can actually work with and control it. For example, a manager might have a mental model of the market to guide economic decision, and an engineer might create a physical model of a building before construction. That this model help to test it, designs, and help to better design. In short, model give us a clear, more manageable view of reality, so we can make better decision and solve problem more efficiently. Type of models. I want to introduce 5 key type of models used to understand and represent reality. First of all is mental model, that personal belief or perception, like someone's view on what caused inflation. Another is descriptive model, qualitative explanation, such as a diagram showing why a student misbehave. Another is physical models, tangible form, like a scaled down city models. Number 4 is mathematical models, formulation, quantifying relationships, such as for example, predicting inflation rate, that I say in first part in mental model. It can be a mathematical model. And the last one is simulations, analyzing feedback and delay, such as balancing electricity supply and demand. I mean to emphasize that all models simplify reality and have limitations. Each type serves a unique purpose, from personal perception to a complex simulation, from mental models to system dynamics models. Now, understanding this difference help in choosing the right model for a given problem. And I should say again, every model has limitations and represent only part of reality. Models are tools, useful but incomplete representation of reality. I want to highlight the critical role models play in decision making, and I should ask why models matter. It's so important question. Models simplify complex realities, enabling individual and organizations to make informed decisions. Without model, we had a struggle with overwhelming complexity in this real world. It's normal that we faced into some challenge when we use of models. For example, inaccurate model lead to poor decision, and another is models must evolve as reality change. Outdated assumption can be harmful. The key insight, the key statement is models are not perfect, but they are essential for action. This statement captures their values. While no model fully represents reality, they provide a structured way to analyze problem and take action. I should say use models wisely, and the wisely way is test their accuracy, update them, and remain aware of their limitation. Okay, I want to define the mental model and their importance. Mental models are like thinking tools we use to understand life and make choices. Everyone uses them, parents, bosses, and even politicians. For example, a boss think if I pay workers more, they will work harder. That's their mental model. A parent believes strike rules make a kid behave better. That's their mental model. What's the big idea? No one makes decision without a mental model, even if they don't release. But these thinking tools are simple, so sometimes they are wrong. If we notice our mental model, we can fix them and decide smarter. Okay, key features of mental model. First, the mental models are fast to make. Your brain create them instantly. And for example, a teacher see a noisy class and think these students are lazy. Another is the mental model are easy to change. When new info comes, your brain updates its rules. For example, the teacher learns that the students are hungry and now think they need food, not punishment. And not always clear. The mental model not always clear. The rules feel fuzzy until you talk or write about them. Mental models are your brain's quick rules that help you decide faster, but they can be wrong. So talking about them help you think better. Mental models are helpful, but they have big limits. Number one, a small brain RAM. Your mind can only handle 3 to 5 things at once. For example, you can't track all reasons for rising prices, just a few. Number two, they are guesses, not facts. Your brain jumps to conclusion that might be wrong. For example, thinking more rain equal more frogs without real data. Number three, stuck in your head. Other can't see your mental model unless you explain it. So, what's big idea? Mental models cut corners. They ignore parts of reality to stay simple. Your brain shortcuts are fast but fuzzy. The mental model are fast but fuzzy. Share them to avoid mistake. How to upgrade your mental models? First, I should say write it down. Your thoughts are clear on paper. For example, a manager lists why they think sales are dropping. Now they see gaps. Another, use other tools. Add numbers or diagrams to your thinking rules. For example, pairing a gut feeling about customers' behavior with the survey data. Another is talk it out. Share your ideas to fix blind spot. For example, a team debates a strategy each person add when the others missed. What's the big idea? Your brain shortcuts are powerful, but combining them with writing tools and team working make them even better. Don't just think alone. Write, calculate, and collaborate to decide smarter. Now we arrive to descriptive model. What are descriptive models? They are written explanation that help us understand complex thing clearly, unlike fuzzy mental shortcut in our head. Why we use descriptive model? Why we use them? First, I think fix mental model's weakness. Mental model can't handle many factors. Descriptive model helps. For example, Marx Capital breakdown capitalism step by step, way clearer than a gut feeling. Now, how they help? How the descriptive models helps? They turn messy idea into a structured analyze and make invisible thought that it's shareable and debatable. Descriptive models upgrade your brain's rough draft into details map, and it's a good thing. Now we want to see why descriptive models beat mental shortcuts. First, handle more info. Your brain can only track 3 to 5 things at once, but a descriptive model can include dozens of factors. For example, an economic report analyzing more than 20 causes of inflation, not just price went up. Another is clearer thinking. Writing forces you to define fuzzy ideas. For example, instead of saying the market feels shaky, you list specific risks like supply chain delays or interest rates. Another is teamwork friendly. Others can see, critique, and improve your models. For example, scientists publish a climate theory and other experts test and refine it. Downside of descriptive models. First, slow to create. Takes years to build a good one. For example, Marx spent decades writing Capital. You can't rush deep analysis. Still guesses, sometimes wrong. Even smart models fail. For example, Marx predicted capitalism could collapse, but it adapted. Long live United States and long live Federal Reserve. Another is words cause confusion. People argue over meaning. For example, 10 Marxists have 20 opinions on what Marx said really. In his book that highlights the diverse interpretation of Karl Marx's works, particularly within Marxist theory. Descriptive models are powerful, but they are not magic. They take time, can be wrong, and need clear communications. Better than mental model, yes, but perfect, definitely never. I want to have a quick comparison between mental versus descriptive models. In mental models, the speed is fast, instant gut feeling, capacity handles 3 to 5 things max in maximum. It's fuzzy. I feel X causes Y, and stuck in your head. But in descriptive models, speed is slow, It need takes research, writing, or another thing, but you can include many factors, and it increase its capacity. It's clear data shows X impact Y, not I feel X causes Y. And team friendly documents, books, and you can share it. For key insight, I should say use mental models for quick daily decision. For example, should I take this job or not? But use descriptive models for big complex problem that you need to have some clearly, and you should notice some many factors. For example, how will AI change our industry? You can't use a mental model to answer to this question, and you need to descriptive models at least. Descriptive model deepening understanding, but you will always need mental model to act fast, because mental model are faster than descriptive model. Now we arrive to physical models, the 3D thinking tools. It's a miniature, touchable version of real-world things, like a dollhouse version of a city or a plastic DNA model. And why? Why we use physical models? We use physical models for seeing the invisible. Hold the water molecule in your hand, or test safety. Crash toy cars instead of the real ones, or save money. Spot design flaws before construction began. You have seen them. You can see the physical models in architects, in chemistry, or car industry, or so on. The key idea is that if you can't experiment with the real things, build a copy you can. This model is great when reality is too big, or too small, or too dangerous. Advantages of physical models. Number 1, see and touch learning. Hold a complex idea in your hand. For example, an architect feels a 3D building model. Safe experiments. Test ideas without real world risk. For example, engineers crash mini bridge to prevent full size collapse. And I think most important reason, save money. Fix mistakes cheaply. For example, car makers use clay models before spending million on metal prototypes. Big idea. Physical models turn what if into let's try without the expensive ops moments. The downsides of physical models. First is size matters. For example, a perfect mini bridge might collapse at full size due to new forces. Another is construction costs. Construction costs that complex model can be expensive. For example, detailed city planning models can cost more than actual buildings, and it is a limitation for physical models. Another is hard to change. Like concrete ideas. For example, want to move a river in your landscape model, time to rebuild from scratch. To me, physical models are great teachers, but they don't always predict real life report cards. And you should use of them when you are testing core ideas, and budget allows for learning money. Where physical model shines. Application of physical models. First is in engineering. Test drive ideas before production. For example, 3D printed phototype of new gadgets. In medicine, practice save lives. For example, surgeons train on a plastic heart before a real operation, and in architect catch problems early. Many building models reveal sunlight or shadow issues. Golden rule is physical models connect a dream to reality, but remember, a small success is not equal to a big success, and always consider the scale effect. At the end, it's good to say that in this model you have real world practice before the real world performance. Mathematical models. I named it the calculator of reality. The mathematical model is a quantitative representation of phenomena using variable, equation, and mathematical relation. Why we use of this model? First, I should say that the mathematical models turn guesses into exact number. What it mean? It means that change this answer probably around to precisely 7e52 meter per second answer. Another benefit is predict future behavior. For example, calculate exact time of reach a rocket in Mars, for example. You can see them anywhere, from climate change prediction and the stock market forecast to space mission planning. And math models are like reality spreadsheet. They don't just describe the world, they let you test it. And I should say, when you need answer in numbers, not words, it's practical. Advantages of mathematical models. First, the mathematical models are accurate and accuracy and clarity. No fuzzy word, just exact number. For example, the temperature will rise 2 and 3 degrees centigrade, not a bit hotter, and it's accurate. Another is internal consistency and no self contradictions. For example, if x is equal to 3 and y is equal to x plus 2, y can't equal 6. It always 5, and 2 plus 2 is always equal to 4. No self contradictions. All things are consistent. Another is high analytical capacity and handle infinite complexity. Process thousands of factors at once. For example, climate models weighing more than 100 variables simultaneously. And the last is open to the critique and review. It means team verifiable. The mathematical models are team verifiable. Others can check and improve your work and say comment. For example, scientists globally test each other's pandemic spread equations. Now we arrived to limitations of mathematical models. First is forced simplicity. Reality is messy, but models need tidy equations. For example, assuming all workers clock 8 hour days when real life has flex time, overtime, and burnout. Another is need for expertise. Only useful if you speak equations. For example, a brilliant climate model helps zero people if no one can understand it. And it's distance from reality. Real world rules change. Models often don't. For example, a supply chain model assuming stable shipping cost failed when pandemic hit, and it's important. I think math models are powerful lens, but they only focus on what their equation can capture. And a smart user always asks, what did this model have to oversimplify, and who can actually explain its result? Okay, we arrived to system dynamics. System dynamics is a time travel simulator for complex problem. For definition, I should say it's a mathematical computer-powered model that show how systems evolve and simulate the behavior of complexity of systems over time, considering relations and feedbacks. 3 points in system dynamics are important. First is nonlinearity, modeling real-world complex relationship. Numerical solving, using computer-based simulation, and feedback-oriented analyzing the mutual effects of variable. Where system dynamics shine. System dynamics can use in various fields, but the most important are climate change predictions, stock market crash, urban planning, pandemics, waste management, for instance, solid waste management, carbon footprint, supply chain management, and many fields we can use of system dynamics. Without any bias, I must say that the system dynamics is an extremely powerful tool. Let me share a memory. I currently live in Iran. During the beginning of the corona pandemic in Iran, one of the most prominent Iranian person in the field of system dynamics, Professor Mashayekhi from Sharif University, presented a system dynamics model of people who will be infected during COVID-19 virus in the future. The results were undeniable. In a time when some people were trying to deny this disease in Iran or treat it with traditional medicine and shamefully violet oil, this prediction could have been a milestone for decision makers. This is one of the million of applications of system dynamics. What's key idea? Unlike static models, system dynamics let you fast forward reality to see tomorrow's consequence of today's choices. System dynamics good for a problem where everything's affected everything else, and you are faced to time delays warp outcomes, and you need to test what if safety. Why system dynamics models are game changers? First is high realism. It handles messy real life connections. For example, simulates how education funding affect on better jobs, and better jobs affect on less crime, and at the end less crime affected on happier cities. Another is flexibility. In system dynamics, you can add new factors like Lego blocks, and it's so easy. Um, Three is scenario analysis. You can try 100 policy ideas without risk. For example, test higher taxes versus spending cuts before voting. The closest thing to a time machine for decision makers is system dynamics, and you can see the future before they happen. I should notice that the system dynamics is more useful for leaders, and leaders use it. For example, in governments, leaders use it will for answer to this question: will this new law backfire in 5 years? Or maybe in a hospital, answer to this question that how many ICU beds we will need next winter. The hurdles of system dynamics model. First is computational complexity. For instance, climate change simulations need supercomputers. Another is need for accurate data for model calibration and other purposes. In the other word, garbage in, garbage out. Bad data outputs bad model and useless predictions. And system dynamics is specialized skills. To me, it's a PhD level skill. For example, building a stock market, the model requires advanced training, and sometimes it needs to an expert team and team working. But despite the challenges, I should notice that system dynamics offer a window into a future that hasn't happened yet. Conclusion: SD is very powerful but needs fuel like data and a trained pilot. This table compares 5 types of models across key features. Mental models are fast and cheap but have low accuracy and handle only 3 to 5 factors, making them good for quick decision. Descriptive models offer better clarity for qualitative analysis and with unlimited factors but take more time. Mathematical models provide high precision quantitative analysis through they are complex and costly. Physical models give tangible, medium, high accurate result for testing, but are limited by scale and expense. And system dynamics excels at simulating a complex system with unlimited factors and high accuracy performance, and perfect for policy testing, but demands significant data, expertise, and resource. I should notice that each model type trades off speed, cost, and complexity for different needs, from snap judgment like mental to long-term forecasting like system dynamics. At the end, I want to announce 3 golden rules make modeling effective. First is pick the right tools. It means that use a mental model for quick decisions and system dynamics for complex simulation and complex forecasts. Second is mix models smartly. Combine descriptive writing with math equations for fuller insights. And third, always reality check. Test if predictions match real world result. And for final message, I want to say models are like maps that help us navigate our complex world. Each offers a different view, but only together do they reveal the full landscape. Okay, it's end. Thank you for watching this presentation. I invite you to subscribe to System Dynamics World on YouTube for more educational videos, and if you found this content helpful, you can continue learning about modeling and system dynamics through this channel.